Well, good morning, everyone. It looks like we have quite a few people here with us. Thank you for being here with all of us this morning. Just a few additional details. We will have a poll or a small survey launch after each talk today. We'll keep it up on the screen for about 2 minutes. We ask that you please fill it out. It helps us for future programming. Another thing to mention are the CCA credits. Those will also be displayed on the screen after each talk, and we will make sure you get enough time to scan those. And then I'm just going to go ahead and jump right into our first speaker of the day, which is Dr. Jason Clark. Jason has a bachelor's in agronomy and a master's in plant science, both obtained from Utah State University. He also has his PhD in soil nutrient management from the University of Minnesota, Twin Cities. And he is currently an assistant professor and SDSU Extension Soil Fertility Specialist. His research and extension education program is focused on determining nutrient management methods that can maintain and increase crop production while conserving and reducing inputs in a way that minimizes environmental impact and is profitable for farmers. And his title today is Corn, Nitrogen, Phosphorus, and Potassium Recommendation Updates.
Yeah, was I going to go first and then Jack and Jason, or
if you want to take it away too, I can introduce you as well.
Okay, yeah, I need to go on to the Watertown Crops Expo here in a few minutes. So yeah.
Oh, well, I apologize. So this is Anthony Bly, and he is the SDSU Extension Soils Field Specialist. So with that, you can go ahead and take it away.
Sure. Yeah. Thank you very much, Shelby. Yeah, dealing with high fertilizer prices, I think, is on the mind of a lot of producers since, this started back in September. We were realizing that fertilizer prices were starting to shoot up and all those questions, and kind of early for most producers, don't even have their crop in the bin yet, and a lot of their economics and budgets straightened out, and they're faced with making decisions on what to do. And so I think it's important that we review what's behind a fertilizer rate, our recommendations from the university. And so I'm going to take about 10 slides and discuss that a little bit. But first of all, here's the NPK prices for the last few years. It's not in any particular reason, but really 2002 there is kind of the benchmark of the old era, I would say, of fertilizer prices, and we can see how really low they are. 21 cents on N, 16p and 14 on potash there in their dark blue. And then in 2007, we seen a uptick that kind of shocked the world a little bit as far as crop producers and buying fertilizer nutrients. That kept on going through 2009 and into 2012. And then we seen a kind of a moderating after the big spike in commodity prices, and it came back down a little bit. And then I got in there that kind of lime green or olive green color there is November of 21. You can see that from the spring of 21, which is kind of the mauve color. That was the first kind of uptick that we had, and then it's just shot up like a rocket ever since. And so currently, and you can argue with these prices. Where did you get them? Because the story is across the region, depends on who you talk to, but by and large, urea nitrogen is around $1 a pound for nitrogen, a unit of nitrogen. And the DAP price is 68 cents for a pound of phosphate and 69 cents on the potash. So we have some critical issues to really think about, because we've never been at this point before. I know the potash is kind of similar to way back when, but I think we're really concerned about that nitrogen price. So when we think about a nutrient rate or the nutrient needs of the plant, most all these nutrients, come from the soil, really. We're really fertilizing the soil, putting it in that medium, and then soil microbiology can deal with it or modifies it, transforms it. There's mineral P and there's mineral K in the soil. And so we're just augmenting that system and building that up and increasing production efficiency is really what we're doing with fertilization. So science, what Jason does and what I did for a number of years when I was on campus, our continual work was refining sufficiency levels for each plant essential nutrient. And really it's based on Liebig's law of the minimum. And so what makes that important is that there's one nutrient or one factor, could be water, could be sunlight or temperature, but there's one factor that really limits productivity of the plant. And that could be a nutrient. And in most cases, those are things that we can control. We can apply more nutrients. And I just want to highlight that soil nutrients do not need to be in balance. We're really concerned about them being in a sufficient level. And this balanced nutrient approach has been disproven many times. And I'm not going to get into what studies and where and how that happened, but we just know that and we can make that statement. So here's that barrel, and yield is the water in the barrel, and then we've got all our factors as staves in the barrel. So the yield is really limited by the most limiting factor, as those staves on the barrel. So soil testing goal is really to identify the lowest stave in the barrel as it relates to scientifically identified sufficiency levels. So we use soil testing to do that, and then we follow what our recommendation is. And sometimes there's more than one. So, there could be 3 or 4 staves of the barrel that are low, and we address all those at the same time. So usually, we do this nutrient sufficiency determination through the research on small plots because we can minimize that variability. Really this is a precision ag technique, and Jason's going to talk about his P&K work. So, you're going to get more of that there as well. And so you can see that we're really honing in on a specific area. We extensively soil sample that. All nutrients except the tested nutrient are applied at sufficient levels, so we know we're testing the nutrient in question. And then a rate of that nutrient is put across that area in a plot sequence with a replicated fashion. And so that's kind of important because we don't want to put the rate on to overshoot the sensitivity of us determining where that yield response is. So I put an example there of phosphorus. The rates are usually 0, 20, 40, 60, 80, what have you. They're not 100, 200, 400, and 800. Yeah, because 100 could be the last point on the graph where we get a response to applied phosphorus, and then we won't be able to determine our sufficiency level. There's always a check plot. They're always replicated, and the goal of the treatment rates are identify a point where no further yield is occurring. Non-mobile nutrients usually have a sufficiency level, while the mobile nutrients we usually develop a coefficient based upon a yield or a yield goal. This is just an example of a plot plan. You can see along the left-hand side, there's reps 1, 2, 3, and 4. I kind of cut off the Roman numeral there. Sorry about that. And then across each rep, you see the plot number, and then you see the nitrogen rate there. And then in this one, there was also a side dress comparison and a urea comparison to Super U. But that's basically what we do. We try to do a number of these, a whole bunch of them. What I did is pulled one nitrogen study out in Huron in 2014, and this is the response of corn to those nitrogen rates across the bottom of the graph. Of course, what I have there is fertilizer plus soil nitrate in the soil, and you can see I've tried to use the linear plateau method there, and it looks like the optimum nitrogen rate plus soil nitrogen was at 165 pounds. And if I use that yield at that plateau, which is 205 bushel, it comes out to be about a 0.8 coefficient. And so I just wanted to build this a little bit to talk about how we get to our recommendations. Here's another site. I believe this is Campbell County. My screen thing's cutting it off, but same fashion. But at this site, the yields are lower. That plateau is lower. The optimal rate there is 145 and the coefficient's 0.94. So you can see they're different. It's not always the same. And that's kind of the point I was trying to make. And here's all of the sites from 1994 to 2018. And it's just a wild, crazy scatter. And it's because our yield levels are different all across the state. Okay, and it's hard to make sense of that. That line is trending up, but I mean, it's not a very good fit to that data. So what we kind of can generally do sometimes is put them all on a relative scale to their own location. And so 100 would be the highest yield at that location. And then we put all that together and we can plot it with a line, and the line fits the data much better. And so you can see that here in this. And I often get asked, well, what about tillage? And so here's a comparison of a conventional till and no-till separated from that data. And you know what? Them lines look pretty darn similar, don't they? So corn is responding to nitrogen similarly, no matter what kind of tillage we put there. The coefficients may be a little different, but the response is still there. Then some say, well, that's really old data. You've got old data. It's not valid. We need to do this again. And we do need to keep doing this. This is an ongoing thing that should never end. But I've divided that data into time periods, 94 to 2003, 2004, 13, 14, 18. And still those lines are pretty similar to each other. We can use that original equation of all the data, and we can apply a economic optimal nitrogen rate approach to it and use the price of corn and fertilizer nitrogen and vary that. And that's what this graph is showing. It's not for you to really use, but it's to give you the idea. And what I've highlighted there at the bottom of the graph, that's 50-cent in and 250 corn. Okay, that's the curve for that. And then the very top one is 20-cent in and $5 corn. And so you can see the differences in response, and the economics really matters. So I separated, I pulled out 4 curves from that data, and it's the 40-cent in at 550 corn, 60-cent in at 550 corn, 80-cent in at 550 corn, and 95-cent in at 550 corn. And you can see on those curves, we want to be at the point where our returns are diminishing. And in fact, when we have very high prices, we want to be even further down the curve. And we want to make sure that we make a profit. And so right now, a 95-cent in and 550 corn, we're at just under 100 pounds an acre. Now, I'm not suggesting that that's the rate you should use, but it's the idea that we should be really concerned, especially this year, about not going overboard and putting ourselves in a loss, immediate loss in corn production. So what I did is went back to that Huron site here and put a curve on there. That curve represents the data pretty well. And those stars on the curve reflect the yield at that point that each nitrogen rate was happening. They were in 40-pound increments, but we also added the soil in there as well. And so the tables to the right show the cost of nitrogen at 60 cents and $1. Okay, you can kind of see that there at that little table at the top. And then the next table below, I calculated the yield increase from each one of them incremental rates of nitrogen. And the first incremental rate at 40 gives us 24 bushels. Then it's cut in half to 12, then 10, 7, and 6. And then I did the income from that yield increase at 525, and I subtracted the cost of fertilizer at the 60 cents and $1. And you can clearly see that we can afford more fertilizer at 60-cent in, but it's much less at $1 in. And so we just want to be make you aware that we're at a critical point with this issue. We've never been there before, and if you're paying $1 for your nitrogen, you might not even be able to fertilize for your yield goal on your farm. So you just want you to be aware of that and help you be as profitable as you can. I think that's my last slide, Jack. Yeah. I'm going to let you go.
All right. Did you need to do a poll thing, Shelby?
Nope. I think once you're
Just-
done speaking, then we'll throw it up.
Yep, that'll be fine. Oh, I gotta shrink some things up here so I can see the screen a little bit better. Don't know if this always works. Yeah, what a rapid increase that we saw this, as Anthony alluded to at his first slide there. And over on the side is your nitrogen trivia from September 1 to well, that should say December. No, actually, I'm sorry, that is November. So that was as November 15th. Anhydrous went up $9.56 a day or 40 cents an hour. And urea was $4 a day or 17 cents an hour between September 1st and November 15th. And these this table of cost of production is from the Iowa cost of production report. So you can see the increases over last year or last fall of 20 to December 28th. This report comes out every couple of weeks. There's an Iowa cost of production report and then an Illinois one. And I just took this data from Iowa, from Iowa's cost of production report. And then I borrowed some slides from StoneX, and I follow a Josh Linville. He follows fertilizer real close, and I've thought his stuff has been kind of interesting. And I know this is a little bit fuzzy, but I think the thing we want to pick out is what he's doing here is New Orleans urea price, which is tracked on the Board of Trade, and then the new crop corn ratio. And if we see for many years or much of the time, it's in that 55 to say 65 range. And now it's up around 135, or futures are saying it's right at 135. So that's crazy. And so as Anthony had said, we're going to have to really do our fertilizer budget, know what we got, know what we're shooting for on the yield goal. Is it going to get better? You know, it has really come down this first week at the Gulf, but boy, it has not come down worldwide yet, and we still need a lot of urea to come to the United States before March. So it'll be interesting how this plays out. And this is just looking at the Arab Gulf difference and U.S. So when it's up, when the red line's up above, we're paying more, and when it's down below, we're paying less than replacement costs out of the Arabs. So we're way below getting more fertilizer to come to the U.S. at this point. But we'll see. You know, these are very high values for this nitrogen. So if the producers of the fertilizer start to panic, thinking that we're not going to buy in the U.S., Brazil, Canada, in the northern hemisphere, or the areas that are going to be planting, they'll want to take some of those profits and they'll panic and start to sell. So, you know, just very much like selling our commodities off the farm, there could be some emotions that run pretty high as we move into spring. So just go through some bullish and bearish factors for urea, phosphorus, and the potash. You know, world inventories are low. So if you think of just like when corn stocks to use ratio is low, anything that happens to disrupt that, then results in a large price increase. The Chinese exports are out. You know, they stepped away at least till probably summertime. The European production was cut back due to high cost of production over there, and they just cut back. You know, either shutting plants down or slowing production, and those take time to get geared back up. And now we got our increased demand coming from Canada, Brazil, and the other areas. So that's kind of a bad blend for price, but we'll see. Because like I said, the emotions could start to run, and if some of those producers of fertilizer think they're going to miss out, they might get in the bidding war, which we would hope for farmers' sake, or at least get this thing straightened out by summertime in next year's crop. Yeah, as I said, low inventories, setbacks will be felt instantly. One analogy would be like, you know, when you're the blocker for going pheasant hunting and you're riding in the back of the pickup, when you feel the bump a lot harder than the front guy does, the guy driving. So it could be rough if we have some type of disruption in manufacturing and or shipping too. Again, North American values way below. World demand is high. We need to start competing and still bring it here. The old analogy that high prices tend to cure high prices. So we could see that play out. And is our urea and nitrogen high enough? Could we see acres shift away from high nitrogen dependent crops into other crops? Probably part of that would be if we saw new crop corn, you know, continue to fall. If that's going to get down below $5, we would easily see shifts, I believe, in our fringe areas of corn production, that people would move away from the high nitrogen demanding crop. And European production, some of that gas has fallen, and they are starting to come back online. China could choose to start exporting at any time. You know, we don't know when that would come. So those would be things that would be bearish. Currently, I think USDA came with their early estimates. Actually, the report that was out yesterday, and they're talking 93 million acres. A lot of the trades thinking maybe some less than that, but yet some is expecting higher. So if that would happen to go, you know, if that bumps 93 up into 94, 95, that's pressure to keep prices higher. But on the other hand, if new crop prices fall or weather turns poor at spring planting, then we could see that demand drop. Switching to the phosphates, China continues to restrict their exports. We had a great fall run, you know, really almost up till the week before Christmas. At least in South Dakota, you could pretty well do whatever you needed to field wise. Those inventories were probably drawn down, and global inventories are still low. Again, China could change very, very quickly. In our corn acres, we don't know what's going to happen there. We have some things that were put in place that made it bullish when Mosaic asked for duties to be put against Morocco and Russia. So that's adding some price. It's not that it would affect the price a lot, but just maybe psychologically, if those would happen to be taken off, that would help the mood and make it feel like there would be more available. Potash, the big thing there, Russia and Ukraine, that if that escalates and they get into conflict, you know, they may stop all the exports from that area. And that's almost a third of potash world trade. So that you take a lot of that off if something happens and that conflict escalates to actual out war. Acreage, yeah, some are estimating that higher than 93. I think our weather plays the big role in there. And the bearish factors, again, the grain prices, fertilizer producers, they increase their production or selling of it because they want to grab market share. Like I said early on in the talk, we're at pretty high levels, excuse me, for all of these fertilizers. So if somebody wants to panic and step in and drop that cost by $50 a ton, and the next one comes in and drops him by 65, and you could get that bidding war. That could take place. And then potash is probably one of the easier ones for farmers to give up, I should say, and possibly not affect yield. So it seems like on the farming and production end, when you get a chance to make a decent profit, all the inputs want to grab their share of it. So watch carefully, do your soil testing, and work your plan, and again, probably be working with your supplier closely to let them know what that is, and so you got your product on hand when you're ready to go. I don't know how well you can see that. Matt Dearson put this together from our trading lab, and I just wanted to show it's new crop. It's a December contract for a bunch of years. So we got a lot of lines going across there, but our big purple one is our high year, which was 2011 and 12. So 721 is where that went off the board. When he put this together, he pulled this for me a week or so ago. And our current price was at 551 then. So we're a long ways where it was from in 2012. Again, emphasizing probably need that management of the inputs. But the same thing going for soybeans. Again, that went off in that 11-12 time period at 14.11. That was its last trade, and it traded well above that at some time. Now we are currently, or when this was put together, we were right at $13. So that it was a week or so ago when he pulled this out for me. I just thought that was interesting, and something that if people wanted that, we could get that graph to you and do a little more study on it. That's what I have. Anthony's, well, I think we roll to Jason now, right?
Yeah. Jason.
So. Go ahead and put up that poll for everyone, and then I will share that CCA credit. And just a quick reminder too, while we're waiting for the poll and the CCA credit, if anyone has questions, feel free to ask them, and we will try to answer all of them for you. All right. So I'm going to stop screen sharing. And if there are no questions, then we can go ahead and move over to Dr. Jason Clark. And I know I already introduced him prematurely, so you can go ahead and take it away, Jason.
All right, thank you. All right, thanks, Shelby, for that. So today we're going to do is go through just a little bit of an update of what we've been seeing with our phosphorus and potassium research that we've been doing throughout South Dakota. And Anthony kind of hit this a little bit, but we see a lot of what this research is based on is these crop fertilizer recommendations. And that's where we're looking at how yield increases from low to high, either on a relative yield or absolute yield basis, versus our soil test levels. And this is where you get your low, medium, high, very high levels. And what we normally see with these is that we see a graph that looks about like this to a certain point in the ideal world, is that at low soil test levels, we're going to have a low relative yield compared to if we did fertilize. As our soil test goes up, eventually we're going to level off here, where if we have higher soil test levels, we're not seeing an increase in yield from adding fertilizer. And the point at which that we level off here is that's where we get these critical values that we use. So for Olsen phosphorus, it's 16 parts per million. For potassium, it's 160 parts per million. So anything below that, we'd say it's below optimum, and you have a good chance for seeing response to a fertilizer application. Whereas above that point, we're above our optimum level, and we'd say you're likely not going to see response even if you add fertilizer to those fields. We've actually seen in some cases, we're seeing a decrease in yield if we still add fertilizer there. And I'll show you some examples today with that as well. So what we're looking at here is this critical value. And this critical value is based on chemical soil tests that we see fairly frequently. And these chemical tests we can see pretty often. There are micronutrients, our phosphorus, our potassium, our pH. However, there's other measurements that we can use when we're looking at soils and we look at frequently. There are physical measurements. These are related to soil texture. They're bulk density, aggregation, soil structure, how well water moves down the soil, as well as biological. We can see different things, and these are some newer ones we hear a lot about. We hear a lot about organic matter, about proteins, respiration, the DNA, the fungi, the microbes that are in the soil. And these three things work together to create availability and unavailability of nutrients in the soil for our crops. So some of the questions that we're working on with our fertilizer recommendations, this is typically what we would see. However, we're wondering that if we have different soil health or different soil physical characteristics, does this change? Does that yield go up faster and we hit up and our critical value actually slides to the left a little bit? Or if we have different poor soil structure or something like that, does that curve actually go out farther and our critical value actually moves to the right? And so to kind of answer this question of how our chemical, physical, and biological factors in our soil are affecting this critical level and our fertilizer needs, we've been doing research the last 3 years. The stars on the map here of central and eastern South Dakota are where those trials have been. We've tried to get various areas throughout the state as different farmers have allowed us to use their land to conduct some of these studies. And so our first one we're going to be looking at is phosphorus. And if we look at the critical value of our phosphorus, it's at Olsen 16 parts per million and Bray phosphorus at 21 parts per million. So that's our current critical value. So here, this is the ideal curve of what we kind of see. Now, what do we see when we're actually out in the field? So here is our yield response ratio. If it's at 1, that's where we're seeing 100% yield at that 0 application level. And here's our soil test phosphorus from 0 up to 80 parts per million. So we're looking at is trying to figure out that curve. At what point does it go up? Does it hit 1? And where does it go flat? So if we look at the actual data that we've seen the last 3 years, it's pretty mixed. However, we kind of do see some trend of some going up here and then leveling off. Our current parts per million critical value is around 16 parts per million. However, if we do some of the math and stats in this, we actually see the leveling off come a little bit later, moving closer to around 24 parts per million. We still need to do some research to see if this critical value needs to change. And this system we've been doing a lot of this research in is conventional and a mix of conventional no-till fields and mostly corn soybean rotations. We look at some data coming out of the peer research station with Dwayne Beck. He'll actually show you with diverse cropping rotations, we might be able to move this critical value from 16 to actually lower. So this phosphorus is pretty dependent on our cropping system, but some of the traditional cropping systems in South Dakota are similar to what the data shows here. And that next question we were talking about is some of these soil health measurements. We have a lot of labs and there are people looking at soil respiration, carbon in the soil, and different things like that, trying to figure out the health, the quality of our soil. So one thing we've been looking at is, can we use these just not only to see the quality of our soil, can we use them in our prediction of yield response for phosphorus? And what we've seen to this point, and just some preliminary data that we've been looking at this past fall, is that if we use that Olsen phosphorus, which is what we traditionally use, and combine it with soil respiration, which is a value or a measurement of how much the microbes in the soil are respiring, how much they're breaking down organic matter and things like that, we can kind of improve that recommendation. The amount of response or amount of increase in prediction we're still working on, but it does show us that there's some promise in being able to do that. So our next one here, we're going to look at potassium. And the critical value for potassium, if we look at this right here, is 160 parts per million. Now, potassium, we have a lot of the same questions. Both NDSU and University of Minnesota have changed their recommendations, some based on soil type, as well as clay type. And we'll kind of look at that a little bit later. And we've been doing some research as well. In North Dakota, they'll tell you that if you have a clay that holds onto your potassium pretty tightly during the year, this 160 parts per million should actually move up to about 200. And we're trying to see if that's true in South Dakota as well. If we just look really quickly at the data that we do have, this is the same graph here where we have our yield response. One is where we see no more increase in yield, typically. And then our soil test levels at the bottom. So if we look here, we can see it's not quite as much of an approach or clear. We see our 160 values right here. We see a little bit of a trend, but our data is a little messy. And the reason it's messy is if you look at this graph here, the important part is we're missing some of these lower values right here. And the reason we're looking at them is a lot of the research we've been focusing on is trying to figure out in these higher rates right here, similar to North Dakota, do we need more potassium? So that's why we have a bunch of sites in this range here, not as many here to get that clear curve. If we were to look at the curve, what we see here, we actually see that that potassium level might actually be able to decrease around 130 parts per million and still not see a yield decrease in our corn yields. So that's a potential there. Before we would officially do anything, I'd want to find some sites. And if you have sites and you're interested in doing some studies, you can definitely do them on your farms. Looking in this area here to see the response of adding fertilizer in lower ones as well as these higher ones. But then going into, so certain soil types, do we need to actually have a higher critical value? Is it over here if I have a certain soil type? So that's going in that question of different soil responses. And what we've seen with the prediction of yield with that is we've seen a couple of things. We've seen that soil test K, but also that clay type that North Dakota's talked about also came out as something that can help us improve our potassium recommendations, as long as with a test called the acid phosphatase enzyme. And that's a measurement of an enzyme that works in nutrient cycling. So that's something that kind of shows us, and this is still preliminary, so we are still working on this, and I'll show you some data from some of the sites we did this summer here in just a second about this clay type function. So with our potassium rates, we have that question, is that critical value need to change on 160? Soil type, clay type, does that matter? And another question I've gotten quite a bit over the last few years is, should I base that potassium recommendation on my base saturation K? Do I need to get that up to 4 or 7%? So that's something we'll talk about this year. So this is what a typical trial, Anthony showed you a map out in a field. This is kind of just, looks like a big grid out there in the field, just a smaller than your good zone soil sampling. These are about 15 feet by 50 feet, and we have the different rates in them and replicated 4 times throughout the field. We also have, these are our rates from 0 to 150. And then we have 2 more treatments. We're trying to move that base saturation K up to 4 and 7%. So if we look at this, this is a field we had in Garrettson, South Dakota, just north of Sioux Falls a little bit. So we have our treatments of 0 potassium, and this is the size of the bag for 30 pounds per acre. So just remember, these are 15 by 50 foot areas of field. That's how much it takes to put 30 pounds per acre on there. And then 60 pounds, we're getting a bigger bag, 90 bigger, 120 bigger bag, 150 bigger bag. And now we're going to move to that base saturation 4% and 7% K levels. So this field right here has a K base saturation of 2.2%. and a potassium of 179 parts per million kind of aggregate there. So here we wanted to see if we're still adding potassium up to move this up to 4 and 7% according to some equations. We'd have to put 1,085 pounds per acre of potassium, which looks like this. You can see how much that is relative to these other rates, or about 1,800 pounds of potassium per acre, a 5-gallon bucket and 3-gallon bucket full of potassium in that 15 by 50 foot area to reach that base saturation K, supposedly. And actually some data that I saw last week from AgVice Labs that looked at this to really truly move that base saturation K to 4 or 7% from something like 2% can actually take you up to around 2 to 4, sometimes 8,000 pounds per acre to truly get it there and actually test your soil and see it a year later. That's some data that I saw in a presentation last week. So it can likely take more than this. And this is kind of, it looks like pink snow out there after you put that much on there. But this past year, we did this research at 9 sites throughout kind of eastern South Dakota, and we focused on eastern South Dakota because this is the area where we have potassium deficiency and where we have those clays that hold on to potassium and kind of create that potassium deficiency, or more likely to find them. So now we're going to move on to some of the data that we've seen in these 9 sites from this past year. So this one is in Hutchinson County. It has a clay loam soil. Soil test potassium around 143 parts per million. K saturation 2%. And this number right here, this is the smectite to illite. These are your clays. And this site is 6.2. The North Dakota data, they kind of use a number of 3.5. If you're above that, then it's saying you would need around 200 parts per million potassium as your critical value instead of 150. So for our site, we're going to say we most likely will see a response here. It's below that 160. But with North Dakota's recommendations, it's saying there's a pretty strong chance that you're going to see one because this has a high amount of smectite. And smectites hold on to that potassium. So here we're going to look at our corn yield, and these are our potassium rates. I just chose a few. This is our 0, our 90, our 120, our 150, and then to move that base saturation up to 4 and 7%. So we'll look at our yield effect here. So we can see, as we would expect, going from 0 to 90 to 120, we did see a yield increase by adding that potassium. We are below that 160 level. However, once we added above that 120 to 150 to 157, we actually saw a little bit of a decrease by adding that much. And at best, by adding about 1,800 pounds per acre, we saw very similar yield to adding 120 pounds per acre in this field. So economically, after 1 year, adding that enough fertilizer to go up to 7% base saturation is not going to pay back itself. This information is only on 1 year. Hopefully we'll be able to get some future years as well. But even with this high smectite to illite ratio, we still didn't see a rate past what our recommendation would be, closer to this area down here. So this is one site, and we're going to look at some other sites. They're all going to be decreasing in this clay content over here that we're going to talk about today. So we're moving to Lincoln County. This is a silty clay loam soil. Soil test potassium is very high at 436 parts per million. K saturation, this site naturally is already at 4%. And that smectite to illite is about 1.5. So here, if we look at the yield response, this is the one site that we saw do this. Even though we do have a high soil test value, we still did see a little bit of an increase in yield on average going across. I doubt this is only a 10 bushel per acre increase, really. So likely not going to be economic to get that yield increase. And going up to 4 and 7%, we saw maybe a 15 to 20 bushel per acre increase. And this site was a little odd. It did have a little bit more smectite in the soil. But this is the one site of the 9 that we did see a little bit of an increase from adding that much. No way that's economic, but we do see some increase in yield at this one site. So in Yankton, on a clay loam soil, still soil tests around 240, K saturation 4%, and that smectite to illite 1.3, so below that 3.5 threshold that North Dakota talks about. So we'll look at what happens at this site. So here we wouldn't expect a yield increase at 240 pounds per acre, or at 240 parts per million soil test level. And that's exactly what we see. We're at the 0 is 192 bushels per acre, the 150, 193. So no yield increase by adding potassium. However, the interesting about this site is when we added up to that 4 or 7%, we actually had a yield reduction of 30 or almost 90 bushels per acre by increasing that soil test level up to that 4 or 7%. And this is one of the sites that we had this to the strongest change here, but you can see how much of a potential effect that is by adding that 4 or 7% potassium on there. And some have hypothesized the reason that this high rates of potassium are decreasing yield might be the chloride levels. I need to look into that a little bit more, or potentially some salt issues at these sites. Now, if we go to Hutchinson County again, this is a sandy clay loam. Our soil that we saw earlier was a clay loam soil, so more sand in this soil. Soil test potassium is 132, so we would expect a response. K saturation is 2%, and that smectite illite is 1, so still below that 3.5. So this is kind of what we see here. So we'd expect a response here at the site. However, we didn't really see one. We went from 161 with a 0, increased a little bit with 90, but not much. And then actually the interesting thing here is once we go past 90, we actually start to see a yield reduction again, and we again see a 15 to 20 bushel per acre decrease when we hit those high base saturation levels to try and move it to 4 or 7%. Now Garrettson, so we're moving a little bit north. This is a silty clay loam, soil test potassium 170. So we would probably say don't apply nitrogen. K saturation 2%. We have a little bit lower, that smectite illite at 0.9. Again, what we see here, we wouldn't really expect a yield increase, and we didn't see one. By adding fertilizer, the 0 was pretty much the same as 120. And again, that same trend, when we have these high soil test potassiums, we actually start to sometimes see a decrease when we start to add too much potassium to that soil. And here again, we're at about a 20 bushel per acre decrease in yield by adding base saturation levels to move it up to 4 or 7%. So here's another site. This is in South Shore, getting the northeastern part of the state. Clay loam soil, soil test potassium 155. So right on that threshold of not needing it. K saturation 2%, smectite illite 0.9. So pretty similar clay content as the last site. And here what we saw is pretty similar results to the last site as well. So we'd expect maybe a yield increase by adding fertilizer, but we didn't see one here in this site. And again, the same trend, once we hit about that 120, 150 range, we start to see a decrease in yield, and we're about that 15, 20 bushel per acre decrease in yield when we hit that 4 or 7% base saturation level. So that's anywhere from 400 pounds per acre of potassium all the way up to 2,000 that we had to apply to hit these rates, depending on the site that we were at. So that's some sites. We did this in 9 locations, and only one that I showed you earlier did we actually see a little bit of an increase by looking at these 4 and 7% rates. Kind of in summary, 2021 was dry, which is most likely where we'd probably see a little bit better potassium response if we did get some moisture. But we really, any site above 150 parts per million, we didn't see a really strong response to potassium fertilization at these sites. And then regarding the question of fertilizing for base saturation, that 4 or 7%, most of the sites, probably 7 out of the 9 reduced yield, 1 or 2 maintained it, and that 1 increased it. So really, for the most part, fertilizing for that base saturation 4 or 7% is not a great idea, especially for South Dakota soils. Places where this works well is in really sandy soils. A lot of people in Maryland will use fertilize based on cation exchange capacity and base saturation, but they have really low CEC soils. So it doesn't take a lot of fertilizer to get up to those levels. So when you do hear those talks about people talking about this, just understand what their soils are and where in the US they are to understand why they might work for them. And a lot of our soils in South Dakota, fertilizing up at that rate doesn't make a lot of sense. So we are looking for more sites to do more of this research this summer. If you have a potassium soil where you think would respond, or you want to learn about the clay types in that soil, let me know. We'll have my contact information here at the end, but we can work on that with you in your fields. We run about 10 different farmer fields last year, and we'll be in similar this year as well. So Anthony already touched this law of the minimum, but I just want to kind of show this. When we're looking at fertilizers and maybe cutting back in different areas, it's really important to know your soil tests. And a lot of times we think of nitrogen as that minimum level over here, as that's usually what causes our leaks. But I'm going to show you a site where it's probably actually the phosphorus with the potassium and not the nitrogen. So just something we have to kind of think about really quick. So this is where our soil test potassium at the site is 120 parts per million. So it's a medium to high category. So likely we should probably fertilize this to improve our yield. However, if we look here at our corn yield down here, and this is our nitrogen rates that we applied. At this site, we saw a typical curve that Anthony showed earlier. And here we see take about 66 pounds of N to reach our optimal yield of 144 bushels per acre. So we get about a 50 bushel per acre increase in yield by adding nitrogen to this site in 2019. So if we take this same field and we move to 2021, we look at our soil test levels, actually it decreased about 110. And what we see here is we see a flat line. We see this is a yield level of 0, is very similar to what we saw here, around 90 bushels per acre. And we see that here as well, except for we don't see that increase that we saw the year before, around up to 150 parts per million. And we actually, I have 2 years worth of data where the same flat line happens. And that's because the soil test level went from 120 down to 110 and about 105 in another year. 1 year was wet, 1 year was dry. And so if we really look at these sites, what we see is that, that 120 parts per million, we were hit there. That was low, but still enough potassium in the soil to increase yield when we added nitrogen. Whereas here we have not enough potassium in the system. That potassium is actually the one being the leak. So the water's running out there. Our yield's limited by potassium, not by phosphorus or nitrogen at the site. So it didn't matter how much nitrogen we put on, we still ended up with no increase in yield. And that's because our potassium and our other nutrients were low. And that's why it's so important to make sure we are fertilizing according to our soil test values, so we don't get sites where we're adding nutrients that aren't paying for themselves by increasing yield. So this is contact information if you're interested or have questions beyond what we have today. We also have the social media, and I'll have more of these results posted on our YouTube page, which is SD State Soil Fertility, and try and put some stuff on Facebook and Twitter to kind of get out more of some summaries from our research results from this past year. That is all I have, and I'm up for questions or whatever else what people might have.
All right, we'll get that survey pulled up as well, and I will get that CCA credit out. There we go. It looks like we do have a question. Marv is asking, can you touch on chloride? I have soils that show recommendations of 15 to 30.
For the chloride recommendations, we don't have much for corn. We have seen some chloride recommendations, especially for small grains, and that helps with the disease susceptibility. They did that research several years ago. So I know it helps with small grains. I haven't done much in relation to corn or soybean. And I'm not sure, is Anthony still around, Jack, or did he take off?
He had to present at the farm show here. Yeah.
Mm-hmm. So that's So with corn, I haven't seen a lot. We have seen potentially that chloride is responsible for some of that decrease in yield by adding the potassium chloride fertilizer, that potash, because the chloride is there. But I haven't done a lot of research with it. I have to, if you want to email me, Marv, I think you're the one to ask the question, and then I can take some time to do some more looking into that for you. As far as the next question, magnesium and calcium ratios are important. I think Anthony touched on this as well, that they've been shown, people talk about them a lot here and there, but we haven't seen, as far as the research goes, it doesn't support those things. We just need really a sufficient amount of magnesium and calcium. The ratio doesn't seem to be as important as the amount that's in the soil.
Right, it looks like there's another question in the chat from Eric. Any work on starter for corn? Been hearing you guys not using it due to both high price and no yield increase.
We have done some starter fertilizer work this past couple of years, and I would have to talk. Peter Kovacs at SDSU is the one who's been working on it. I've worked with him some, but I haven't seen results from the past 2 years. He's presented work on the split applications he's been working on, and I have those. But I'd have to get back to you, Eric, on what some summaries as far as that goes in regards to them. Mostly with starter applications, it works best in cold and wet spring. So when we have that, you see results from starter fertilizer applications. And when you are warm, like it was this past year, and drier, we don't see as much response. But I can see what Peter's found out last couple of years and get back to you as well.
Okay, well, if there aren't any other questions, just like to say thanks for attending again. Please look for an email from us at the end of the week with the survey attached. We appreciate your evaluation. And please join us next week. We'll be covering a variety of different soybean topics, including different varieties, management techniques, and weed control.